So here we are talking about using statistical software and summarizing data, and this section is about types of data. And in this section, we're going to talk about the quantitative and categorical data, interval scale and ratio scale. And this is going to be very important and very interesting to understand what are the different types of data in this section. So let's start off with quantitative and categorical data. So it is important to know what type of data we are handling in research, because it all depends on knowing what type of data we are handling, the analysis, the interpretation, the type of test that we're applying on it, and how we are handling it, how we are manipulating it and analyzing it. It all depends on knowing what type of variable it is. Secondly, categorical data are sometimes also known as qualitative data, because it is relating to some quality of any variable. Let me give you an example. For example, gender, either male or female. So being male or female is quality of an individual, and that is why it is a categorical variable and also known as qualitative variable. Now, this term is rather ambiguous because it gives rise to a misconception that the data collected from a qualitative study, that is known as a qualitative data. But that is actually not the case. Qualitative data is something which actually reflects or tells us about the quality of any individual. The data that we collect from qualitative studies, such as in-depth interviews, are actually something different because they are not in this section. Moreover, quantitative data, on the other hand, is information that can be measured and written down with numbers such as length, weight, height, anything which can be measured on a scale or something like that and interpreted in terms of numbers. Now, let's start off with quantitative data. So data that can be measured numerically, and it may be continuous or discrete. So as I gave you an example, for example, measuring length is quantitative data, and length is a quantitative variable. And now this can either be continuous or discrete. Continuous means like length is continuous. 1.1, 1.2, 1.3 centimeter, it can be anything. But discrete, for example, if I talk about visual numeric rating scale, so it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they are discrete values, 1, 2, 3, so there's nothing in between. But if I talk about visual analog scale, so it is a continuous variable. Now, lying on a continuum, and so can take any value between two limits, that is the property of quantitative variable or quantitative data. Only isomerization is that imposed by the accuracy of the method of instrument. For example, if I talk about length, now I'm measuring length in terms of millimeters, and I have a simple scale or a ruler. Now it cannot measure quantity less than 1 millimeter, which is the least count for it. So I'm measuring length, and it would give me length in the form of 1 millimeter, 2 millimeter, 10 millimeter, 15 20 millimeter, 25 millimeter. But these are all discrete values. So does that mean that it is a discrete data or discrete quality? Not necessarily. It is actually because of the accuracy of the method of instrument. On the other hand, if I'm using a screw gauge or a vernier caliper, it can give me smaller value than millimeter, and I can get a value like 1 point something in terms of millimeter with a screw gauge or a vernier caliper, but I'm measuring the length. So variable is the same, but I changed the instrument, and that actually changed the quality of the result that I'm getting. Now, continuous data may be recorded as integers, and it may appear to be discrete data, and that is an approximation to the true value, as I gave you in the example of a scale or a ruler. They do not lie on a continuum and can only take certain value counts, that is in terms of integers, such as in the example of the scale or in the example of visual numeric rating scale that I already gave you previously. Moreover, if we take the example of weight, it is a continuous variable, and number of siblings, on the other hand, is a discrete variable, because you cannot have 1.5 siblings. You can either have one sibling or two siblings. But weight can be measured in, for example, 34.56 kg. So that is the difference between continuous and discrete. Now, interval scale, when you talk about continuous variables, they can either be in the form of, or we could talk about quantitative variables, they can be either in the form of interval scale or a ratio scale. So what is an interval scale? Such a scale in which differences between values at different points of the scale have the same meaning. So if there is, for example, a man and a woman, and the weight of the man is 70 kg and the weight of a woman is 50 kg, they both gain 1 kg of weight. So meaning is exactly the same, even though their starting weights were different. For the guy or for the male, it was 70 kg, and for the woman, it was 50 kg, but both gained 1 kg of the weight, and regardless of their initial weight, the finding is the same. They both have gained 1 kg of weight. The other type is the ratio scale. And if the ratio of two measurements has meaning, then it is a ratio scale. For example, one person's weight loss was twice that of the other. It can be, for example, one person lost 5 kgs and the other person lost 10 kgs. So one person's weight loss was twice that of the other. So it can be comparable. So it means weight can also be taken as a ratio scale. Now this would have an interpretable meaning, so it makes sense, and it is a ratio scale. On the other hand, let's take an example of temperature, which is not a ratio data. And why is that? Because we cannot say that one temperature is twice hot or twice cold as another. For example, 30 degrees centigrade is twice of 15 degrees centigrade. But if we convert it into Fahrenheit, then 30 degrees centigrade would not be the twice of 15 degrees centigrade, because 30 degrees centigrade in terms of Fahrenheit would become 86 and 15 degrees centigrade would become 59 in terms of Fahrenheit. So the temperature in its true sense is not doubled, and it does not have an interpretable meaning, so it is not a ratio scale. Now, sometimes a data can have a specific order, like an ascending order or a descending order, and that type of data is known as ordinal data. So data values can be arranged in order from smallest to largest, and that is known as ordinal data. Quantitative data are always odd. Questionnaire skills data are often ordinal and are often counts as well. Like if I'm using a questionnaire such as NAC disability index, so it is also quantitative and ordinal. Interval and ratio scale data are also always ordinal. So it tells us that quantitative data is always ordinal. It has an order because 5 is greater than 1, 10 is greater than 5, so it has an order. In practice, however, continuous data may look discrete because of the way they are measured or reported, such as I gave you an example of a scale which can only calculate the length in terms of millimeters and not smaller than that. Moreover, another example is gestational age. For example, gestational age is reported in whole weeks appears to be discrete. For example, 10 weeks. But it is also possible that there may be a case, for example, here we have 38 weeks, for example, and there may be a case that there would be 38 weeks and 3 days. So it is not necessarily discrete, but we were interpreting it as so. So we can also report to a greater degree of accuracy and in a true sense a continuous variable instead of a discrete variable. It all depends how we are presenting the data, calculating the data, and analyzing the data. All continuous measurements are limited by the accuracy of instrument, as I already gave you an example, and many quantities such as age and height are reported in whole numbers, either by rounding off or either by dependency on the type of the instrument by which the data was collected, in whole numbers for convenience. Categorical data may also have an inherent ordering, and can be ordinal, such as stage of disease, like stage 1 cancer, stage 2 cancer, stage 3 cancer, and stage 4 cancer. Now, stage 4 cancer is more severe than stage 1, so it has an order, even though it is not continuous variable, even though it is not quantitative variable, it is a categorical variable, but still it is an ordinal variable, or it is an ordinal data. Now we have talked about the quantitative data. Now let's focus on the categorical data as well. Now, as the name suggests, categorical data in which there are categories. So data which divides the individuals, or in which the individuals fall into a number of separate categories or classes, that is known as categorical data. And these categories can be 2, 3, 4, and so on. Such as, in an examples which are mentioned here, gender is a categorical data because there are 2 classes or 2 categories, male and female. Similarly, disease status, alive or dead, are similarly 2 categories. Stages of cancer are 4 categories, and marital status, married, single, divorced, widowed, or legally separated, 5 classes or 5 categories. But these categories can be ordinal or they cannot be ordinal. For example, if you look at the stages of cancer, there is an order because stage 4 is greater than 3 and 3 is greater than 2 and so on. So it is an ordinal data as well. But marital status, it is not an ordinal data. Similarly, male and female is not ordinal data. There's also dichotomous data. It is actually categorical data, but in the sense that when there are 2 categories only, then that is known as dichotomous data, and the individuals fall in either one of those 2 categories. It is also known as binary data in addition to dichotomous data. So here we have another example. So these are the individuals, and they are divided into 3 categories: no response, moderate response, and good response. And that's an example of categorical data. Now we can also give order to categorical data, but it is important to understand that ordering the categorical data does not necessarily mean that it is going to become ordinal. So different categories of categorical data may be assigned a number for coding purposes, like 1 for male and 2 for female in terms of gender. And similarly, in stages of cancer, 1, 2, 3, and 4 for the 4 stages of cancer. So such data is ordinal but not interval, because the distance between adjacent categories has no measurements attached to it. So you cannot say the gap between stage 1 and 2 of the severity of the stage of the cancer is the same as 3 and 4. No, it is not obvious. So it is not an interval scale. Moreover, apparently similar gaps between categories may not have the same clinical meaning as well. So they may look the same, but the clinical meaning may not be the same. And at the end, calculating a mean of the stage or category for a group of individuals will be nonsensical, because it is not an interval scale, it is not a quantitative scale, it is not a continuous scale. So it is nonsense to create an average that mean of the stage of cancer of the participants. So it may become 3.5. Now that doesn't make any sense, because there are only 4 categories and 3.5 does not fit in any of them. Now, it is also important to distinguish between ordered and non-ordered data, as I already mentioned, such as gender, it has no order, but stages of cancer, it has order. So categorical data can be ordered and ordinal and non-ordinal. So where categorical data are coded with numerical codes, it might appear that there is an ordering, but this may not necessarily be. So if I give code 1 to male and 2 to female, this does not necessarily mean that it is an ordinal data. For example, marital status, on the other hand, may be coded as 1, 2, 3, 4, and 5, but it is not ordinal once again. Now, categorizing continuous data, it is surprising, but it is true that we can also categorize continuous data, like we can convert continuous data into categorical data. So it is possible to reclassify continuous data into groups. But there are some consequences of categorizing continuous data and some drawbacks as well. Those include, first of all, that dichotomizing, or you can say categorizing continuous data, is potentially very problematic because a great deal of information is lost and discarded. Moreover, statistical power is lost in the analysis. Nature of any relationships may be masked because you cannot perform correlation. And relationship, if there was any relationship which was curved, it may become weaker, and if there was any relationship which was U-shaped, then categorization completely obscures the result of it. Now, moving on, if we classify it into several groups, then that is somewhat better because that has a lesser effect on the statistical power. So if you are categorizing the contents data, don't dichotomize them, instead reclassify them into several groups. Grouping causes no problem if the classification is done simply to present summary statistics in a more simple manner. And you also have the original data in the form of continuous variable or the quantitative variable, which you are analyzing for the analysis for other things as well. Then it has no issue, and in fact, it is even better. It is also useful to reclassify continuous data into several groups where we are examining a non-linear relationship, such as analysis may be straightforward and more meaningful if the data is grouped and easier to understand and clutter-free. So that was all about this section. I hope you learned something new out of it. Keep on watching sqadia.com for more lectures like this. Thank you very much.